Actually, I know I said we were going to do conversions, but I lied. Actually, I just completely forgot. We have to do scientific notation. So we have to talk about scientific notation before we get to conversion. So apologies. That's not how you spell notation, is it? That's notion. So oops. So let's fix that, right? So notation. And I normally just write psi not here, okay? So I'm very lazy. I don't want to write things out in full. But scientific notation is really useful for writing very large and very small numbers. So, for instance, we can have the number of atoms there are in a charcoal briquette, and it looks something like this, and this, and this. Let's see, this, this, this. I think this is right. Hold on a second. Yeah, so this is actually a pretty typical number here. So this is the number of carbon atoms in 12 grams of carbon. It is also roughly equal to the number of atoms in my cup of tea. And it's also very roughly equal to the number of stars in the universe. So it's pretty amazing that if you look at 12 grams, that's about half an ounce of carbon. So that's about, take about a dozen pencils and just take the leads out of the center. They're made of pure carbon pretty much. And they have the same number of atoms in as there are stars in the universe. And we can convert this to scientific notation. And I always think about it as karaoke, actually. And so in scientific notation, we always write a number. So I'll write n, and then we times it by 10 to the plus or minus another number. And all we got to do actually to get scientific notation is we have to move the decimal point until we get a number between 1 and 10. And if we look at this number here, so this number up here, the reason I said it's like karaoke, you remember in karaoke where the little dot goes underneath the syllable that you're supposed to be singing. So all you got to do really is just karaoke in your mind the number of times you got to move this decimal point. So we don't always write it out, so you got to know where it is to make a number between 1 and 10. So that's 3, that's 6, doink, 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 that's 9, 12, 15, 18, 19, 20, 21. That would give us 600. So 22, 23 would give us 6.0. Or just 6. So we actually write this in scientific notation as 6 times 10 to the, and the thing is, how do you remember if it's plus or minus n? So what is n here? N is the number of times you move the decimal point. So I've moved it 23 times, and I always remember actually that it is positive when it is a number bigger than 1, and it is negative the number of times I move the decimal if the original number is less than 1. So this number here is absolutely massive, right? I mean, this is, what would this be? 1,000, million, billion, trillion, 1,000 trillion, million, trillion, billion, trillion. So 600, billion, trillion atoms there are in just 12 grams of carbon. So 600 billion, trillion stars in the universe. And this would be a very big number, right? Much bigger than 1. So we would write 6 times 10 to the positive, the number of times we moved it. So positive 23. And we don't really need to write the positive in, but why not? Let's do it for fun. So this is a very big number. We'll see later on, we call this Avogadro's number. And we're going to count atoms using multiples of this number here. We'll call it the mole. And remember we did those 7 base units, and one of them was chemical amount. And we said the mole is the unit there for chemical amount. This is why. So you could just say, well, that's just silly. Let's just use regular numbers like 12 and 100. But unfortunately, you get numbers like this 600 billion trillion. And you have to ask yourself, do you really want to say 600 billion trillion? Or do you want to say 6 times 10 to the 23 or 1 mole? And it's much easier to talk about a mole than a number, so that's why we're going to do it. So let's go ahead and go to the next slide, and I'll tell you the diameter of a hydrogen atom. So if you have a hydrogen atom, and hydrogen is the first element on the periodic table, it's got, rather than a diameter, it's got a radius, and the radius is equal to 0.0000000000. I think that's right, 594 of a meter. Let's say, did I do that right? We're going to say I did. And we can do this in scientific notation by moving the decimal. Now, because this number is much smaller than 1, right, it'll be something times 10 to the minus the number of times I move it. So because the original number is smaller than 1, right, instead of being positive, it's going to be negative. So I move it 3 and 6 and let's see, 9 and, well, that's not right, 6 and then 10. So this would be 5.94, right? Because that decimal is now all the way there. I've made a number between 1 and 10. So times 10 to the positive 10 or negative 10. Well, if the original number is smaller than 1, it's negative the number of times I moved it. So it's 5.94 times 10 to the minus 10 of a meter. And actually, I did it wrong. That's actually not the radius of a hydrogen atom. That's actually too big. And so it's actually 10 times bigger than it should be. So the real radius is actually 0.0000000000594. So you sound like a dork, right, when you say these regular numbers out. So, but it's really easy in scientific notation. So there's 3, there's 6, there's 9, there's 10. That gives me 0.594. So there is 11 steps, right? So the number would be 5, it's got units, 5.94 times 10 to the minus 11 of a meter. So 5.94 times 10 to the minus 9, or sorry, 10 to the minus 11 of a meter is the radius of a hydrogen atom. So you can see we deal with very large and very small numbers. Now you might say, well, we could just use SI prefixes there, right? We could make it, 0.0594 times 10 to the minus 9, so 0.0594 nanometers. And we could do that as well if we wanted to, but scientific notation is kind of cool, so we should use it, I guess, just for fun, to show off, right? So significant figures, right? So you might say, wow, we did that a couple of videos ago. Why are we doing that again? Well, in scientific notation, we are going to use significant figure rules, and we have to know how to apply them. Now, you might take that radius of a hydrogen atom, and you might say, well, how many sig figs is that? And you might think, oh no, I just have to rewrite that number, so 0.000, and apply the rules. And you can do it that way if you want to, but it turns out in scientific notation it's way, way easier, because if it was like 10 to the minus 280, you'd fill up like 4 or 5 lines writing that number out. So all you got to do to find the number of sig figs is look at this front part of the number here. So this part basically you can ignore, and this part just gives you the number of sig figs. So if you've got 5.94, all of those are non-zero, so that would be 3 significant figures. So here's one for you to try. Maybe you have a number. Maybe it is 1.10 times 10 to the minus 1,028. I don't know. Kilograms? I'm not sure that's too small, actually. I'm not sure you could measure that. How many significant figures would that have? So pause the video and count the number of sig figs, and do not write this number out in full or you'll go crazy. All right. Okay, you unpausing? So how do we do this? Well, for ease, right, that times 10 to the minus 1,028, who cares? That's just moving the decimal point. It is not changing the number of sig figs at all. But we've got the 1 and the 1 there, so they're definitely significant. Is that 0 on the end significant? And the answer is only if there's a decimal point. So since it's 1.10, that decimal point means it is significant. So we have 3 significant figures here. So notice that gives us a way to write numbers. So for instance, let's say we had a number like 2,800, and we wanted to write it to 3 significant figures. And you might say, well, you can just write it 2,800. Well, that has 2 significant figures because those zeros on the end are not significant. So maybe you try 2,800 period, right? And you go ahead and you count sig figs now. So those zeros on the end are now significant because of the decimal point. So now you say it's got 4 significant figures. And if you're like, oh no, right? So I can get it to 2, I can get it to 4, but how do I get it to 3? And the answer is we need this 3rd digit here to count. So I'm just going to go ahead and underline this, okay, because I want that one to count. And I can play the karaoke game. So there's a decimal point that's implied. I got to move it 1, 2, 3 times there. So I can write that number as 2.8. Okay, times 10 to the, is it positive 3 or negative 3? Well, if the original number is bigger than 1, then it is positive the number of times we move it. So it's positive 3, or I'll just write 3 for short. And again, that's got two significant figures because the 2 and the 8. And if I needed to have 3 significant figures, I could just take that third 0 there and I could write it in. And so it would be 2.80. I'm sorry, I used like a highlighter pen there. So 2.80 times 10 to the 3. And now I would have 3 significant figures. So sometimes you have to get a number of significant figures that is quite hard to write out in a regular fashion, and scientific notation comes to the rescue